Good evening, ladies and gentlemen, and as well as a good evening to those people in the room, a good evening to those in the overspill area as well. And a very warm welcome to the Royal Society of Edinburgh. I'm Ewan Brown, its Treasurer. Many of you know us well, but for those who are less familiar, we are Scotland's National Academy of Science and Letters. We are multidisciplinary with around 1,500 elected fellows who are all experts in their respective fields. The RSE is proud that the advancement of learning and useful knowledge has been its priority for over 200 years. We continue to support the very best of research being undertaken in Scotland, and through the engagement of our fellows to deliver a wide range of public benefit activities for the benefit of Scotland. We have a number of close associations with other learned societies, and one of our valued relationships is with the Royal Academy of Engineering, with whom we are happily joined at the hip this evening. The Royal Academy of Engineering promotes the engineering and technological welfare of the country. The fellowship, comprising the UK's most eminent engineers, provides the leadership and expertise for its activities, which focus on the relationships between engineering, technology and the quality of life. This is the 18th annual lecture co-hosted by the two National Academies. It takes place during Science and Engineering Week, principally an English event, and is used as an opportunity to engage members of the public who might not otherwise attend a scientific lecture and enthuse them about modern science and technology. It's also an opportunity for engineers based in Scotland to get together. And so to tonight's subject, the Twin Towers, 10 years, 10 lessons on sustainable infrastructure. I'm sure that in the last few days we've all been affected by the stories and pictures from Japan. And over the years, the world's media have brought us many other disaster events where structures have been rent asunder. However, the images that are indelibly imprinted on our memories are of 10 years ago. Aircraft flying into the World Trade Center, the vast dust clouds as the huge buildings collapsed, and the grotesque shapes which remained. Our expert speaker is Professor Torero a fellow of both academies. He was made a fellow of the RSE a year before the Academy of Engineering, I'm delighted to say, who leads a group of fire safety engineering experts within the Institute of Infrastructure and Environment at the University of Edinburgh. He qualified in engineering in Peru before moving to the University of California to complete his PhD. Lecturing and research positions in France and the USA followed before his move to Edinburgh 10 years ago to head up the Building Research Establishment Centre for Fire Safety Engineering. We are not expecting a building collapse here this evening. However, in the event of any emergency, please leave by the nearest fire exit and assemble outside the George Hotel across the road. The lecture has been recorded and an edited version will appear on the RSE website in approximately 2 weeks' time. The lecture has also been filmed for educational purposes only by an Edinburgh University PhD student, and this will be used on the university website and also the websites of the two academies. To anyone who hasn't, please switch off your mobile phone, and please welcome Professor Torero.
Thank you very much for the introduction, and thank you very much for the invitation and the opportunity to talk about the subject that I think has marked the lives of many people, and I think has really marked our profession in fire safety engineering deeply. And so it's the 10th anniversary of the World Trade Center failures this year, and I think before I get started, I want to emphasize what the subject of this talk is, and so that you don't sit there under the misconception that I might be talking about conspiracy theories, because I will not. This is not intended to be a technical talk that is going to explain in every detail why these buildings collapsed, although I'm going to touch a little bit on the subject. I think it's more a thought process, is the idea of trying to understand how we extracted out of this failure a series of lessons that will enable us to do a much better job as engineers in trying to design buildings to sustain a fire. So the basic principle behind this talk is fundamentally trying to understand what we have learned, and maybe at some point it might sound that what I'm saying is a little bit negative, because you always hope that you learn more out of these things, so you take the most advantage of these tragedies. But I think it is important to reflect on the things that we have not learned too. So within the lessons and the things that we have learned, I'm going to embed some of the big question marks that still mark our profession and have been made very evident by the failures of the World Trade Center. I don't know if we can put the lights down. Thank you. So, basically, this is World Trade Center. These are the images that has been said marked people's vision of September 11th, 2001. I think most of us remember these images. We remember the impact of the aircraft. We remember the subsequent fire that eventually triggered the collapse of the first building and sequentially triggered the collapse of the second building. So there's also within the compound of the World Trade Center, there's also two other collapses, a very small building, World Trade Center 5, that collapsed internally and brought the building down. And then there's the massive collapse of World Trade Center 7, which is a 47-story building that was ignited with a number of small fires, a consequence of the debris that came from World Trade Center 1 and 2. So there's really no reason to linger more into the events themselves, because I think the events by themselves are something that remains within our memory and is very difficult to forget. So I'm not going to talk about the sequence of events or what happened, but basically what happened after September 11th. I think we found ourselves with this. So this is basically the image of the day after. This is the image of the failure that we need to reconstruct. This is the image of the failure that we need to learn from, and this is really what we're working with in trying to understand what we're doing right and what we're not doing right. So in a way, this magnitude of event, this level of catastrophe, is something that many times we argue in communities like the community of fire safety engineering, that this is what we need to wake up. When we're walking towards a precipice with our eyes shut, this is the kind of things that will open our eyes and remind us of the way of which direction we're walking to. And in a world that claims to be, striving towards sustainability, our hope is that we're not going to design by disaster. Our hope is that we're going to design in a way such that actually we can predict the consequence of our actions, before this actually happened. So I think that the real theme or the real subject behind this talk is fundamentally that transition. The transition of design by disaster. Once you have a disaster, you learn of your mistakes and then you build something new. Into how do we actually shift that into thinking of a problem ahead in such a way that this kind of things are not going to happen. That is what we believe is sustainability in a field like fire safety engineering. So, nevertheless, the failures themselves are really important. They're an important aspect of engineering, and it's something that we really need to consider in a very careful way. When we have a failure, we are deeply encouraged to learn. The bigger the failure is, the bigger the disaster is, the more of an effort we're going to make to try to learn from that failure, the more of an effort we're going to try to make to understand what brought us to the failure. So the truth is that at the end, a failure analysis, or the analysis of the failure, is going to provide us with all the information that will enable us to see the causes. It will give us a clear idea of what our mistakes are, And it will allow us to develop new methodologies that can prevent the repeat of that failure. So the fundamental objective of a failure analysis is to be able to get as much information as we can, so we can prevent this type of situations and avoid this kind of tragedies happening again. And the truth is that much of engineering sits on this kind of failures. We've learned from aircraft crashes, we've learned from train derailments, we've learned from collapsing buildings, we've learned from bridges falling down. A lot of engineering actually relies on failures to wake ourselves up, to open our eyes and allow us to start reflecting. But the key part of understanding a failure is the failure analysis. If we don't do a proper failure analysis, if we don't have the tools for a proper failure analysis, the tragedy is wasted. And this is the one thing that we have to try to avoid. This is the one thing that we deeply have to prevent, because given that the tragedy is there, the failure has to be able to enable us to understand what were our mistakes. So in a way, this is, again, the line of thought of this presentation, is understanding from the failure analysis, understanding from what happened in that day, and understanding from our current practices how we actually design buildings better. Is engineers learning from the disasters, and this is really what we would like to do. So the problem in this type of situation is that when you're looking into a disaster like the World Trade Center, it's a combination of a number of different things. It's a combination of the actual physical event. It's a combination of our perception of the nature of the event, and it's a combination of all the politics that are associated to an event that was so visible and that was originated in a political issue. So the investigation in this particular case was a very difficult investigation that required the handling of so many things that in many cases prevented really the true understanding of the problem. So the investigations in general were all conducted in the midst of a lot of controversy. And we can Google World Trade Center, and we're going to find out that there's as many websites discussing all the political aspects, all the conspiracy theories, as you will find that discussions of the events or the technical aspects of the events. So in a way, we have to keep in mind when we think of World Trade Center the context, because without the context, it almost seems that everything that we did since 2001 was mistake after mistake after mistake. Now, the truth is that the context disabled a lot of the things that we should have done, but nevertheless, we had to cope with it because it was a political context that we could not change. So, the truth is that from the beginning, there was numerous amounts of independent studies. From the day after the collapse of World Trade Center, there were papers being published left and right from people with great credibility, but truly did not understand the problem. So you will find journal papers of physicists talking about that these buildings had to be demolished because they collapsed, they fell down too fast. Nonsense. You will find professors from very sophisticated universities talking about how the steel melted in this building. Absolute nonsense. If you hear about people talking about massive explosions that actually weaken and destroy the building, that's absolute nonsense. You hear about people talking about the impact of the aircraft hitting the buildings and damage them to a level that the buildings were going to collapse anyway. That was maybe not nonsense, but not the right explanation to the problem. And like that, there will be numerous amounts of studies that you can find everywhere, and discriminating from the studies that actually have some understanding of the problem with those that have no understanding of the problem was very, very difficult from day one. The truth is that once the events are looked in some detail, it is perfectly clear that these buildings were designed to withstand the impact of the aircraft, and they did. These buildings were designed to deal with all the mechanical constraints associated to this particular event, and they did. These buildings collapsed fundamentally because of one reason: the fire. Okay? And it was not the fire of the kerosene of the aircraft, it was the fire of the furniture inside the building. So that was the main reason why the building came down, and very rapidly we came up to that conclusion. The first official report that comes out is a FEMA report. So it comes out in May 2002, just less than a year after the events, and it basically looks into all the details of the information that could be gathered up to that point. First mistake. all the materials that were gathered through this preliminary investigation of the World Trade Center were disposed incredibly rapidly. When we actually analyzed an investigation of an aircraft, for example, crash, like TW-8800, for example, it took years of collection of all the information, the reconstruction of the aircraft, the looking in detail into every piece of the puzzle before a conclusion could be made. In this particular case, in a few months, all the materials that were associated to this investigation were disposed. Now, conspiracy theories? Trying to avoid seeing the truth? Not really. Fundamentally, it was a political context that really required to move forward. We couldn't look backwards and keep all these remnants as an evidence of something that we did not want to have at that point. So there was a need to move on. There was a need to actually look forward. And therefore, as fast as we could gather information to try to look into what had happened in that day, we had to dispose of all that material. And yes, a mistake. In retrospect, yes, because we could have learned a lot more from a deeper analysis of all the debris, and we didn't. But there was a lot of information that was gathered, and a preliminary analysis was made, and some preliminary conclusions were achieved in this FEMA report. So the FEMA report was followed by commissioning the National Institutes of Standards and Technology in the United States to convoke what they called the National Construction Safety Team Advisory Committee, which was a group of experts from around the United States and a couple of international experts that basically gathered together to look at the problem and make recommendations on what should be the way to follow. The conclusion, the rapid conclusion of this advisory committee was that it was absolutely necessary to conduct an exhaustive investigation of the World Trade Center. The FEMA report was not sufficient. It was too preliminary. The analysis was not complete. We had to use every tool that we had available to conduct an investigation of the World Trade Center. So the United States government produced the funding, and a NIST was commissioned to conduct a 3-year investigation on the collapse of World Trade Center 1 and 2, which were the two big towers of World Trade Center. So they delivered their first report in September 2005, and this was delivered among great controversy. They utilized most of the tools that were available at the time. Science was pushed outside the bounds that we had before September 11. But many people criticized, both in the professional communities and outside the communities, the outcome of this report. Now, it was criticized at two levels. It was criticized at the technical level because the tools that were handled did not manage to deliver a proper reconstruction of the event. The sequence of events that led to the collapse could not be reconstructed by means of the tools that were available, and therefore NIST had to use whatever they had in hand and try to patch it in whatever way it was possible, so that they could actually come up with some form of a comprehensive explanation of what had happened. But the truth is that that comprehensive explanation was really not that comprehensive, and despite the fact that they had put every piece of information that they had available, there were thousands and thousands of hours of film that were analyzed, photographs, whatever was available, it was clear that the tools that were used for the analysis were not capable of delivering a full comprehensive answer of what had happened. So among the technical community, there was great controversy when this report was delivered. And also within the political context, there was great controversy, and many people actually claimed that this report was biased by the fact that it was funded by the US government. Now, was it biased because it was funded by the US government? That's something that I'm not going to discuss, but nevertheless, that was part of the controversy and gives you a sense of all the pressures that were put in the delivery of this type of work. Now, following the report of World Trade Center 1 and 2, there was another report that came out in November 2008, which was a subsequent investigation of the collapse of World Trade Center 7. So World Trade Center 7 was an adjacent building, a 47-story building that collapsed during the fire, because of a fire, and there were no casualties in there, so it was a much more sterile, less political, and therefore less visible investigation. So very few people actually really know much about World Trade Center 7. Nevertheless, NIST came up with a fairly comprehensive report that once again had the same weaknesses. The report did not provide conclusive answers because fundamentally the tools that were used were not capable of developing a comprehensive investigation of such a complex form of failure. So, nevertheless, NIST was compelled to produce guidelines or to produce best practice recommendations, and they came up with a document in April 2009 that puts forward a series of recommendations that are intended to basically redefine the way we design tall buildings. Once again, in the midst of great controversy. And these recommendations keep coming up, and we see them left and right, and international standards and codes have adopted some of these recommendations and modified them to try to improve the state of the buildings. And American codes have done the same thing, and many people have taken the material within the NIST report to provide some clear guidance on how to design modern tall buildings. So that's the history of the investigation. That is basically the sequence of events that represent the failure analysis of the World Trade Center. Now, the most important thing of that investigation, from my perspective, are the goals and objectives. Now, the goals and objectives were very clearly defined. When we look at the NIST goals, what they said is that the objective was to investigate the building construction, the materials used, the technical conditions that contributed to the outcome of the World Trade Center disaster. That was the objective. That is a true and proper objective for this type of failure analysis. That's what we want. We want to understand how this building came down and what are the things that contributed to the final outcome. So the objectives were very well set. And basically, they were set on the basis of trying to create improvements in the way we design buildings, we construct them, we maintain them, and we use them. Once again, absolutely correct goals and absolutely correct objectives. So the result should be improved tools, guidance for industry, and safety officials who are to approve these buildings. Once again, the right things to ask. And like that, every single line that came within the goals is exactly what we want. And the truth is that the way these committees were set up, the way these investigations were set up in a manner such that they were to deliver what we needed from them. Now, unfortunately, when we look more at the detail of the objectives, and then we start looking into the details, determine why and how World Trade Center 1 and 2 collapsed following the initial impacts of the aircraft, that's where the weaknesses come up. Because how do we do this requires us having all the tools that we need to be able to analyze the information that we have. And when you're going to the point where you want to make sure that you understand if the casualties or injuries should be less or more, depending on the context, all of a sudden you start requiring a level of refinement and a level of detail that our tools at the time did not seem to be able to provide. And we need to determine procedures and practices that we use in the design, construction, and operation of these buildings, and basically how do they affect the outcome. Once again, the consequential analysis, what happens if I do this? What happens if I design the building this way? Will it have led to the same outcome? Requires a much deeper analysis than the one we were capable of doing at the time. So at the end, we try to link all this with codes and standards, and once again, I think, and you see as I move through the presentation, this is probably the weakest part of the objectives. So you had the great goals, you have the great ideas, but when you try to implement them, you did not take into consideration the tools that you had available, nor the fact that what you were trying to change was maybe not the right thing to change. When we're talking about fire codes, standards, and practices, I think the vision that this group had of what they were trying to change was probably not the right one. So, on the other hand, here you have an investigation, good or bad, set in whatever ways we can. That's what we had, and that's what we were doing in 2002. In the meantime, life goes on. Now, this is what's been happening in our world of tall buildings. If you look at the top 10 buildings, the highest 10 buildings in the world, 8 of those have been built after 2001. If you look at the top 100, you will easily go above the 40 top buildings being designed and built after 2001. So we are trying to understand what made these buildings fail. And in the meantime, we're building more complex, taller, more sophisticated buildings every day. So this is what industry does, this is what evolution does, this is what innovation does. We have to move on. And we didn't move on only on height, but we also moved on complexity. This building, if you look at it, it has certain particularities. First of all, it's a tall building. Second, it's the most inclined building in the world. All of a sudden, you're introducing structural constraints that are extremely unique. You're pushing the envelope in what we had been doing in the past. Buildings like this are not built every day. Nevertheless, buildings like this are built more and more often. Now, inclining this structure like this, does it make it more vulnerable to fire? These are the kinds of questions that we need to ask ourselves. When we design and build the World Trade Center, we design and build it on the basis of certain criteria, certain rules, certain codes, certain standards, certain tools. Okay? Nevertheless, those tools, codes, standards, and criteria failed on us. Okay? Now we're building a building that poses all sorts of new sets of questions. And we truly are in a position where we really do not have the answer. But life goes on. Not only we do that, but for example, we're using these curtain walls. Curtain walls represent a very interesting fire problem because in a way they create the potential of gaps between the floors and the wall that enables the fire to grow very fast. And we've seen that in a couple of tragedies in Shanghai and the CCTV towers in China just recently. So not only we are putting curtain walls, but we're creating double skin facades. Why do we do that? Because of sustainability, energy conservation. These are the drivers of our industry. Fire engineering is this little. We're being pushed around left and right because people want green buildings, they want energy conservation, they want to put energy generation and put a huge turbine on top of the building. The considerations on fire safety engineering come after we have to try to come up with answers. But we are in the middle of trying to ask ourselves the questions. We have a tragedy, we have a disaster that we did not predict. We have a disaster that actually questions the core of our understanding. Nevertheless, these are the things that we're putting up. Can we stop them? No. Okay? And that's the key. At every level, a building like that represents a new challenge for us. And we're building all these things as we're asking ourselves all the real questions that actually determine the core of our understanding of how buildings should be put together. Now, we understand what we were doing. We were investigating a problem. We understand that life has to go on, and people are setting new challenges before we have even understood the old ones. But at the same time, we had a profession that in 2001 was confident. We had a profession that had grown through decades of real science, of real understanding, of real development, to a level of confidence that allowed us to liberalize all our codes and standards. We allowed performance-based design. What does that mean? We opened the door to engineering solutions that were not prescriptive. We were not putting a set of rules. We were not giving a set of lines that people had to follow. We were telling engineers, use your tools and give me the adequate level of safety. You are an engineer, you're a professional, you can do that for me. So we were a confident profession that had capitalized on 2 decades of unbelievable research. It was prolific in nature, lots of government funding, lots of effort to try to develop the science that will underpin the tools. And that science delivered the tools in the 90s. We opened the door to use engineering in this field, and all of a sudden September 11 happens. So when September 11 happens, we had great confidence in what we were doing. So we refused to believe that what we were doing was wrong. As a profession, we looked at the collapse of September 11th and we blame it on everything but us. And this is one of the real key elements of why this investigation was so complicated. We as professionals refused to believe that our mistakes were the ones that brought those buildings down. So the confidence was so great that we truly believed that all our tools were sufficient to try to understand the problem. we had a flourishing engineering practice that was growing in an enormous way, delivering services all around the world and producing wonderful buildings like the one I showed in that image before. So everything, in one way or another one, was going in the opposite direction. Fire safety engineering was integrating itself into all the other engineering disciplines. We were providing optimized solutions. We were making our protection leaner and leaner and leaner to deliver, the requirements of cost, the requirements of sustainability, the requirements of energy conservation. We were doing everything that we were asked because we felt that we had confidence in our tools. The problem is this, how do you conduct a failure analysis in the midst of a period of great innovation that is pulling us at a speed that we cannot control, with strong technological, environmental, and economic drivers, extremely strong, because markets were booming, everybody was building great buildings, and everybody wanted to have greener and greener buildings, and everybody wanted to have cheaper and cheaper buildings. So all these drivers were extremely strong, together with a profession that was immensely confident on its tools, and an industry that needs to move on. This is the problem that we faced on September 11th, 2001. How do you put an investigation to try to learn what brought those buildings out when all these drivers are pushing you so fast that you don't have the time to think? So let's look then, what did we learn? Because we did the investigation, we had to carry it, good or bad, whatever way we had to do it, it was done. And there were several lessons that could be drawn out of that investigation. So I'm going to go through one by one what I consider to be the main lessons associated to the World Trade Center. Now, lesson one is sustainability. We had to redefine the concept of sustainability. We had to think of sustainability in a way that is different to the way we had thought it in the past. Sustainability for us is our capability to manage the life cycle of infrastructure, where proactive decisions are made to reduce consumption and negative impact from the inception of a project to the disposal of the infrastructure. Think of the concept. When you do prescriptive design, you have a set of rules that you are applying, and you are assuming that the building will behave correctly. A sustainable building requires us to explicitly demonstrate that the building is going to perform correctly. Now, World Trade Center did not do that. That explicit analysis that showed the performance of World Trade Center in the event of a large fire was never done. It was a building that was designed in a fundamentally prescriptive way, where we assumed that the building was going to work correctly. So we clearly identified that the way we had been putting buildings together was not consistent with our goals of sustainability. So at the end, when addressing fire, tall buildings need to be designed to embrace these principles. So we have to move towards performance assessment. We have to move towards being able to understand how these buildings work. Prescription is not going to do that for us, especially when we're dealing with tall buildings that are complex and they're unique. So we need to be very careful that if we really want to think of sustainability, fire safety needs to be an integral component of the frame of designing sustainable infrastructure. So the first and most important lesson that we learned at the beginning was that this event showed us that we were designing, our practices of design were not considering in an explicit way sustainability, and we need to bring that into the design process. Now, the second lesson that we learned was the application of that. So basically, prescription versus performance. Now, what is prescription? Prescription is basically looking into buildings, seeing buildings that are fundamentally homogeneous, that have so many things in common that I can classify them in a way such that the same rules apply to all of them. So I can more or less establish that these buildings work correctly, and once they're classified, then I can say, if I use this set of rules and you follow the rules strictly, I can more or less guarantee you that these buildings will work. Nevertheless, there's never an independent analysis of each building to establish its true performance. Now, performance design is a design that uses all engineering tools to try to look in a proactive way how this building is going to perform. Now, if the building cannot be classified, if the building is unique in nature, then we are required to do a performance analysis. We have to be able to establish if that building is going to be safe. So this question comes up. What are tall buildings? Tall buildings are by definition unique and innovative. They're optimized structures, and therefore they require, by necessity, some form of performance-based analysis. Now, World Trade Center epitomized innovation. It was an absolutely innovative building from beginning to end, from its architecture to its structural engineering. Everything about that building was innovative. What did we do? We did performance-based design for everything. We did performance-based design for wind. The first wind tunnel that was used for a tall building was used with World Trade Center. So we did a very clear establishment of what were the loads imposed by the wind. We looked at the connections, we looked at the foundations, we looked at every detail, trying to establish in a very clear way what was its performance. What did we do with fire? We went 100% prescriptive. We ignored completely the fact that this was a unique and innovative building, and we assumed that by applying the same rules that apply to any other building, this building was going to stand. So we tried to classify this building within a context to which this building truly did not belong, because it was a perfectly innovative building. So fundamentally, the last decade has been a period of great innovation. So the lesson that we have to extract out of this here is that tall buildings are innovative, they are unique, and they are different. So if we're going to use prescriptive design to design all these buildings, we are ignoring the potential weaknesses and failures that could be induced by our new ideas, by our innovation, by our sustainability, by our use of new materials, and by all of these things. So there's a big lesson to be learned there. The fact that these tall buildings can, in the case of fire, have to be designed in an explicit manner. Now, third lesson, sustainability requires optimized design. Now, this is very important because when you're looking into sustainability and trying to minimize consumption, trying to minimize energy, trying to conserve as much energy as you can, you also have to include fire, and you have to integrate all this in an optimized manner. So the only way you can do this is by means of putting fire safety into the design process in exactly the same way. Now, the World Trade Center did not optimize fire safety, it slapped it on. Basically, the building was finished, it was done, it was completed, and what did we say? Let's put fireproofing on it, let's delay the heating of the structure, and it'll work. We believed it will work, but it didn't. So we didn't optimize fire safety into the design process, and we made a big mistake by not doing it. So the failure to understand the structural behavior in fire resulted in the disproportionate failure. That was the key. It was the problem was that the structural engineers did not understand fire. They designed the building for everything else, and they delegated fire to the prescription. The architect prescribed a thickness of fireproofing, end of the story. There was never an analysis that actually was done to show truly how this building was going to perform structurally in the event of a fire. Now, tall buildings are by nature optimized structures, and therefore their design needs to incorporate fire safety as an integral part of the optimization process. If we don't do this, then the buildings are not going to perform adequately, they're not going to be optimized, and therefore they're not going to meet the goals of sustainability. Let me give you an example of what really happened. Okay? So if you look at the way we design buildings, basically we created this curve. Okay? This curve is what we call the standard fire, and it's a normalized curve by the Americans, by ISO, by British. Everywhere in the world, you know, from Chile to China, you will find fundamentally the same curve. So what is this curve? It's a standard fire. It's a curve against which we're going to test our structural elements. What does it represent? The worst case fire scenario. We run a whole bunch of experiments, tests, and all the temperature evolutions of this fire fell below this curve here. Okay? So we can argue that this curve represents a worst case scenario. Now, our knowledge has shown us that maybe it's not necessarily the case, but within the confines of most of the things that we do, fundamentally it does represent to some extent a worst case scenario. So now we take this curve that represents the worst possible fire, and we reproduce it in a furnace. So we make a furnace, follow that temperature time curve. Okay? And in that furnace, we're going to stick a structural element. And the structural element, because it's heavy, because it has a mass, is going to heat much slower than the furnace. And eventually it's going to reach some sort of critical temperature that is going to bring us to what we call the fire rating. So we can say, for example, that if this structure fails at this point, then I will go to the next 30-minute below and say that the rating of the structure is 30 minutes. Okay? If that is less than what prescription requires, I will put insulation to try to delay the heating and bring the failure temperature to a much longer period of time. The World Trade Center was designed, some of their components, to withstand 3 hours, 180 minutes, and other components to withstand 2 hours, the smaller minor components, 120 minutes. This didn't work. Now, the question is, the buildings failed in less than an hour. So, is it the problem that our fire was not a worst-case scenario? That's what people will argue. They will say, well, kerosene fire, very large fire, extremely hot temperatures. Completely false. That fire was actually a very moderate fire that was well within the context of this worst-case scenario. It was not the fire. The fire was not as big and as hot and as deadly as people thought. The fire was an office fire that was well within the constraints of the problem. Now, what was the problem? The problem was the structure. It was the innovation that was embedded in the structure that fundamentally changed this. Now, this critical temperature is defined on the basis of material properties. Basically, when steel heats up, its resistance drops. So when it drops to 50%, I define it as my critical failure condition. Okay? Completely arbitrary of the design of the building, completely unrelated to how I put the building together. In the 90s, we learned that it's absolutely critical how you put a building together to define what this failure temperature was. So relying on our prescription is fundamentally, is that me? So relying on our prescription was a problem. We should have not relied on this critical temperature, and this was the weakness of the design. So if I look at the problem, basically what was the problem? The problem is that you had a very rigid set of columns on the outside, a very rigid core in the middle, and a very lightweight slab in the middle. This enabled building this building. This was a technological innovation that enabled to put this building fast, cheap, economically, and providing these open spaces that were very desirable. So fundamentally, it worked as a structure. But what happens when you constrain completely something that is very lightweight? As soon as it starts heating up, it tries to push its way out, and it can't, because it's restrained by very rigid columns and a very rigid core. And because it can't, it buckles. So at the beginning, it's trying to push the columns out, so you can see how the columns turn bending out. But then eventually, when it fails, it brings the columns back in. There's no controversy on that. We understand that now. We've learned that with the World Trade Center. So we've learned that that was the failure mode for these buildings. Now, if you look at these photographs, you will see it. Earlier in the fire, you can see how these columns are being pushed out and the covers of the columns are falling off because the floors are trying to expand and trying to push the columns out, but they can't. Later in the fire, you will see the opposite. Now the floors are sagging, and you can see how the columns are bending inwards, and eventually that's what will bring the columns to buckle and the building to come down. So you can see NIST did this reconstruction where they aligned every single one of the columns and showed the deflections. Early on they were outwards, later on they were inwards. And once, at the moment when the collapse was triggered, you could see how these columns were moving inwards in certain areas of the building. There's no controversy on this. We understand that that is the failure mechanism. The details are very difficult to understand, but the fundamental failure mechanism is well understood. But this is a part that very few people understand. Now, if you actually look at this building with no damage, with the actual fireproofing, this is the intact building. This is an engineering analysis that was done on the intact building that shows that this particular building had a massive vulnerability. Because the nature of the structure, when you actually analyze the range of collapse and no collapse, you can see that if a fire extends for more than 2 floors, your failure temperatures are not not 500 or 600 as your materials should give you, but they're actually going down as low as 400 or even less. Now imagine what happens when you add the dislodgement of the fireproofing and you add the damage that was introduced by the aircraft. This curve probably shifted even lower. And that clearly explains why these buildings came down much earlier than what they should. So this is the part of the analysis that makes you truly understand what are your design weaknesses. This was never done for this building. It was done for wind, it was done for foundations, but it was not done for fire. So we ignored completely the fact that how you assemble the building is going to determine the fate of the failure temperature. It's not how big the fire was, it's not how complicated the fire was, it is fundamentally that we ill-defined the failure temperature, and we ill-defined it because we did not understand the global behavior of the building. So there you go, very good lessons learned. Now, we've learned lots of this. The science has improved enormously through the investigation of the World Trade Center. We've understood the role of connections and how this particular type of connections weaken the building even further. We understood, for example, the role of fireproofing and what happens when you dislodge the fireproofing and the quality, what is the importance of having excellent quality fireproofing. We understood, for example, in World Trade Center, the problem of asymmetry. NIST will claim that because this building here is asymmetric, once this starts heating in this corner, this girder here will be pushed outwards, will be dislodged from its connection, resulting in the failure of the floors that eventually triggers the collapse of the building. Controversial? Yes. Complete? Yes. Incomplete? Yes. It's an incomplete conclusion. Nevertheless, it is a clear evidence of the things that we have learned in the process. In the past, nobody would have ever thought that an asymmetry and the failure of a single connection could bring down a 47-story building. Today, we actually do believe that that might be possible. Once again, a very important technical lesson that we've learned through the World Trade Center. So there's a lot of technical lessons that basically enforce the idea that if you want to have sustainable infrastructure, fire needs to be included in an explicit way. Now, the problems need to be understood and resolved by means of the most adequate methodologies, and once again, this is where we found ourselves in a problem, because World Trade Center demonstrated that egress is very important. We need to get people out, and that structural performance are the pillars of fire safety, because if the building comes down, I will never be able to get the people out. So I have to guarantee that people can move through safe paths, but also that the structure remains in place. The problem is that for tall buildings, egress is extremely slow. A rule of thumb is about 1 minute per floor. A building that has 110 stories will take you at least 2 hours to evacuate. So if the structure is not designed to withstand the fire until the fire burns out, the structure is going to collapse with people inside the building. In tall buildings, the overlap of times between egress and structure is completely coupled. In smaller buildings like this, you can exit in 1 minute while your structure has not even begun to heat up. In tall buildings, the two things are absolutely linked, and they cannot be separated. The problem is that I cannot speed egress. I can't, because it depends on how fast people can move. And no matter how big I made the paths, it's going to reach a peak, and that's the speed at which people move. Now, the problem is that life goes on. And unfortunately, innovative structures need a proper engineering analysis because they do not conform to standard practices. So I need to do a structural analysis to guarantee the second part. But because life goes on and people have to move, what did I end up focusing? We ended up focusing on egress, when the truth is that we have very little to gain with egress. A lot of the recommendations, a lot of the changes that have been implemented in the last 10 years have tried to guarantee a better form of egress, and we have somehow closed our eyes and ignored the fact that it is the structural integrity what truly matters in this particular case. So our focus basically is on egress, and we have ignored that in the absence of an adequate structural design, enhanced egress capabilities gain you very little. So at the end, the safety of tall buildings requires explicit structural analysis, and we have decided to completely ignore this, and most of our changes, as you can see by NIST's recommendation number 17, are focused on accommodating the best possible egress. Yes, we want that. Okay, but it's not the problem we're trying to solve. The problem we're trying to solve is better designed structures. So this brings us to lesson 5. So lesson 5 is fundamentally the one that breaks the problem. There's no well-defined responsibilities. The architect is supposed to define the fireproofing, the structural engineer is supposed to design the structure. Nobody designs the structure for fire. So at the end, the implicit assumption that thermal protection is going to fix the problem is wrong. Nevertheless, that's what we rely on. Now, for tall buildings, the structural engineer needs to assume responsibility for the adequate performance of the structure in fire. That is an important lesson that we've learned. If the structural engineer doesn't assume the responsibility, there will never be a proper designed building for fire. Innovation introduces complexity, as we've seen, and thus the drive for sustainable tall buildings is introducing fundamental changes in the structural design, material selection, and potential fire conditions. Once again, we go back to the uniqueness. The World Trade Center demonstrated that to be able to establish an adequate fire safety strategy, there is a need for professionals of great knowledge. People need to be able to understand the behavior of structures in fire. Okay, and the level of knowledge that is necessary for that is extremely high. Now, sustainable tall buildings require the involvement of professionals with that level of competence. Okay, and in the design of a complex and comprehensive fire safety strategy, we have to involve people that understand things. Now, what did World Trade Center did in its investigation? It basically questioned the competence of our engineers. We were confident. We thought we knew what we were doing. But the truth is that what does a structural engineer need to know to be able to properly design a building with fire? In 2001, we did not know. We had no idea what a structural engineer needed to know to be able to design a building properly for fire. Neither did we know what a fire safety engineer had to know to do the same thing. The two of them were designing their parts of the building. There was no integration of the disciplines. Everybody thought they had the problem under control. Nobody did. Okay? And that is a fundamental weakness that was unveiled by the investigation. We start pointing fingers at each other, saying, you don't know what you're doing. Everybody start complaining. There's so much controversy on the technical knowledge behind that investigation. Why? Because we don't have a proper definition of who really knows what they're doing. So, at the end, the World Trade Center investigation made very clear that the framework that we've been using to educate professionals to design tall buildings is inadequate. We need to be able to integrate this profession so the communication can be done in an adequate way. Now, this framework is designed to operate within a prescriptive environment where things can be just simply boxed. The architect defines the fireproofing, the structural engineer does everything in code, and the fire safety engineer designs sprinklers and smoke detectors. Okay? That's what we were doing. We boxed people there, and we ignored the fact that these buildings require the integration. So, the current framework is not suitable and it's not sustainable, and we need to change it. The problem is that if we're to strive for sustainable infrastructure and all the associated innovation, we need integrated professionals. We don't have them today, and our educational framework does not deliver it. So we're getting to the end of the story, and we're beginning to realize what the big problem is. The problem is competence. At the end, the World Trade Center showed that we lacked an adequate definition of competence. That really ends up being the end of the story. We did not have a proper definition of competence, or who should be doing these things and how they should be done. Our current definition of competence not only leaves enormous knowledge gaps, but also is structured around the incorrect objectives. It's structured around an objective of solving individual problems and not solving the integrated, explicit performance of the building that is what is going to give us sustainable infrastructure. So we not only have no definition of competence, but we're looking in the wrong direction. So at the end, the development of sustainable tall buildings needs a new definition of who's competent to deliver the engineered fire safety strategy. We don't have that today. After 10 years of World Trade Center, it's completely obvious that we need it, but we don't have it. So, lesson 9 is extracting from a failure all the knowledge that will enable professionals not to make the same mistakes requires a minimum level of prior understanding. Now you know where I'm getting to. So the truth is that the unprecedented magnitude and the novelty of the World Trade Center failure caught us by surprise. We thought we knew everything, and we knew nothing. That's the truth. We were boxed in our own ideas, and we never understood the complexity of the integrated analysis of buildings. So at the end of the day, we were communities that were fully unprepared to deal with this particular type of investigation. So unfortunately, we wasted a tragedy. We had a tragedy that really is going to be something that is going to mark us forever. Nevertheless, we did not have the knowledge to be able to tackle an investigation in an adequate way. We fell in all the cracks of our gaps of knowledge. We fell in all the cracks of the lack of framework to try to analyze these things. And there we are at the end, after 10 years, basically with more questions than answers. So the challenge is the gaps of knowledge are now evident. So we know where all the holes are. That's what we did in our investigation, identify everything that we didn't know. Yes, a great thing, because at least we know where the gaps of knowledge are. The future of tall buildings design, unfortunately, depends on our capability to continue filling those gaps faster than what technology evolves. We are this big. The construction industry is massive. They're moving so fast that we're clearly not keeping up. So this hope that I put in here of being able to move as fast as our capability to innovate is a hope that every day I wake up in the morning asking myself, how much terrain have we lost today? And I seriously do not have an answer for that. So that basically brings me to lesson 10 and the end of this story. So the World Trade Center showed that if we want sustainable tall buildings, we need to develop the knowledge base and the technological tools that can adequately assess the performance of a fire safety strategy. That is absolutely necessary. We need to incorporate this knowledge not by legislating new rules, which is what we've tried to do to make the apparatus continue to move. We've thrown rules here, we've thrown rules there, widen the stairs, add more fireproofing, do this, do that. That is not going to work. A building whose structure is poorly designed is a building that is vulnerable, that is weak, and the event of a fire has an unpredicted behavior. Okay? So that is not going to work. The only way to fix this problem is through an adequate professional structure within a relevant definition of competence. Today, we don't have that. Our definitions of competence are not adequate and they're not relevant to the problem that we are addressing. So we need to legislate, promote, and invest in competence, not on standardized solutions. Thank you very much.
Richie, who is also both a fellow of the Royal Society of Edinburgh and the Royal Academy of Engineering, to provide a vote of thanks.
Thanks, Ewan. Yes, and in fact, I'm a council member of the Royal Academy of Engineering as well, and we're very proud in the Royal Academy of Engineering of this series of talks that we do every year, and it's a great testament to that we have speakers such as Professor Torero. The Royal Academy is building a couple of things in Scotland at the moment. We have a development of a Scottish committee in action, and we're actually building relationships with the Royal Society, which I think is very valuable. We also have a proactive membership committee that started in Scotland, and we're building our membership here as well. So the Royal Academy, I think, is doing its bit to increase the general understanding and knowledge of engineering in Scotland. Professor Torero's presentation tonight was very appropriate. He mentioned earlier this evening before we came in that it was his great-grandfather who emigrated from Scotland to Peru, and he's found his way back here, very much because he chose this area of fire safety engineering, and the place where fire safety engineering discipline is most developed is here in Scotland. There's been a chair of fire safety engineering for over 30 years in Scotland. One of the very first in the UK, and it's a very important centre for this. So it's quite appropriate that we have this presentation from him here. The heritage of this whole subject in Scotland is very relevant. Obviously, the talk tonight is about the 9/11 event, and that's probably one of the very few events that most of us will remember where we were when it happened. I think we all have it imprinted in our brains that day, and particularly the images of the firemen going into the building, and then the collapse of the buildings, awful. But fascinating insights, and I have to say it's been very illuminating this evening, learning the fact that, I mean, I would have assumed that a 767 going into a building would automatically wreck the building, but the fact that Professor Torero says no, in fact it wasn't. That wasn't because of the failure, and the burning of the kerosene from the plane wasn't enough to actually do the damage and so forth, and it could have been avoided. Absolutely fascinating insights into this. So his lessons is that fire safety needs to be built in to this, the sustainable performance of this type of engineering. Egress can't compensate, and the complexity of buildings might not be helping, but actually you've indicated that the complexity might be a solution to this, and that the simpler buildings might actually be more susceptible to failure, and a more complex building, but understanding the fire implications would be the right approach. But I suppose the most chilling thing that you've told us tonight is that we haven't really learned the lessons, and that's a worry, because engineering does move forward when failures happen. So you've set a very good challenge to us all to try and build this type of fire safety approach into our engineering from now on. So, a fascinating talk, I'm sure you all agree, and can I invite you to join us with, and thank Professor Torero for his very illustrated talk. Thank you very much.